Hello students, welcome to JCE Connect series of lectures. So in previous lecture we have solved some of the examples on curved vanes considering stationary as well as moving. So in this particular lecture I'll be taking one more typical case, that is a jet striking a moving curved vane tangentially at one of the tip and leaving at the other. So in previous lectures and all, we have taken a moving case also, where the jet was striking at the center and the vane was moving in the direction of jet, and there the vane was considered placed symmetrically about the x-axis, and here the vane is being considered unsymmetrical case, and the jet is striking tangentially at one of the tip. So this is the case where I am considering in this particular lecture, and this case to be solved by using a velocity triangle concept. So this velocity triangle concept which can be used mainly in turbo machines. So what are turbo machines? A turbo machine describes, that is machines that transfers energy between a rotor and a fluid, and which includes both turbines as well as compressors. While turbines transfers energy from fluid to a rotor, whereas a compressor transfers energy from rotor to a fluid. So in these turbo machines, they could be a turbines or a compressor to analyze the fluid force, or if you want to calculate the force exerting by the fluid or work done by the fluid, so we have to use the velocity triangle concept. So what do you mean by velocity triangle? A velocity triangle or a velocity diagram is a triangle representing the various components of working fluid in a turbo machines, and velocity triangle may be drawn for both inlet and outlet sections of any turbo machines, and the vector nature of velocity is being utilized in this particular concept. The vector nature of velocity is being utilized in these velocity triangles, and the most basic form of velocity triangle consists of the absolute velocity v1 and the blade velocity, that is u1, and the relative velocity vr1. And as we know from the previous lectures, so a jet was impinging water on the blades like this. So this is the rotor or impeller of the turbine, since we are considering the turbo machines, and the jet is impinging water on the blades. These are the blades mounted on the impeller or a rotor, and the impeller is in turn coupled with the shaft. When the jet strikes the vanes, this vane starts moving in the direction of the jet. In the direction of jet. So then next again this will move forward with the velocity u. Then the next blade will come and stand before the jet. Again that vane also receives the force by a jet, then that also moves forward. Then the third blade will come and stand before the jet, that also receives the force and moves forward, and this will continue. Hence the force is being transferring from jet to the vane to the impeller or a rotor to the shaft to the generator, hence the production of electricity. Then for the analysis of forces or the analysis of velocity, how the velocity is being changing at every stages, because before coming out of the nozzle, what was the velocity? Then once it comes out of the nozzle, what could be the velocity? Then the moment it hits the vane or the blade, what is the velocity in the blade passage? Then when it is coming out of the vane, what could be the velocity, and how it can be represented? So that can be represented by drawing a velocity triangles at inlet as well as at outlet. Okay, at inlet as well as outlet. So and typically, as I said, this velocity triangle consists of absolute velocity, that is 3 component, and the blade velocity as well as the relative velocity. Then, as you know, see this this is the vane. You can say it is a one blade. So I have taken one blade I am taken. So here one blade I have taken. So what happens here, when the fluid entering the vane, see this is a jet is striking tangentially like this. This is the vane, and the vane starts moving in this direction. So as the fluid entering the vane and it glides over the surface like this, it will glide over the surface. As it is doing like this, there is a change of momentum. Either there is a direction, or that is either there is a direction of fluid, or both magnitude and direction of fluid are changes. Means here you can say a nozzle, the jet is coming out of the nozzle. This is the nozzle, and from the nozzle the water is coming out with a very high velocity, a jet. It produces a very high velocity jet. When it enters into the blade passage, okay, it will come out with the velocity v, and this is also moving, but it enters with relative velocity. Okay, so how that can be that relative velocity or the absolute, this is called absolute velocity. Then next comes, this is the blade velocity, then next comes the relative velocity. How these all can be drawn by using the velocity triangle concept, we will see later. So as it enters into the blade passage, what happens here, the momentum of the either there is a direction of the fluid, or both magnitude and direction of the fluid are get changes. So there is a change in the momentum of the fluid, what we get. Then water will be passed through the nozzle. As we are passing through the nozzle, when it comes out of the nozzle, it will come out as a very high velocity jet and impinges on the blade. When it impinging, it will move over the blade passage, and there is a change of momentum what we get. Then the fluid momentum that will be transmitted to the blade passage, because water is gliding over the surface, and the fluid momentum that will be transmitted to the blade passage, that is or some amount of force will be exerted on the blade passage, and the blade will move in the forward direction, in this direction. Then another blade will come and receives the force, as I explained earlier. See here again, in this case, as the fluid is striking the vane, then the water is gliding over the surface like this. So as the fluid is gliding over the surface, there is a change in the momentum, either the direction of the fluid or both magnitude and direction of the fluids are get changed. And because of the change in the momentum, this blade receives the force. And as it receives the force, then it starts moving in this direction. Then again the next blade will come and stand before the jet, that also receives the force. Again the third will come and stand before the jet, that also receives the force. So this continuous rotation will go on, and ultimately from the blade the motion will be transmitted to the disc and shaft. That is, this is the disc, we can call it the disc or a rotor or impeller, and the motion will get transferred from the blade to the disc and disc to the shaft. Then from the shaft we will get the output in the form of electricity. That is how it works. And if we have to do some analysis, we have to see how the fluid velocities are being changing at every stage, and what are the different components of the fluid velocities. That component can be drawn in the form of velocity triangles, and these velocity triangles are being used to find the force exerted by the jet and work done by the jet. And here we have drawn the velocity triangles like this. So like this, you have to draw the velocity triangle like this. So initially first you look at the inlet velocity triangle. So we have drawn the section of the nozzle here. You can see here we have drawn the section of the nozzle like this. This is the pipe. This is section of the nozzle. From the nozzle the water is coming out the very high velocity and hitting the blade. So here the blade is placed. We have taken one blade. Okay, so we have taken one blade and we are analyzing the fluid velocities here. Okay, so we have drawn the section of the nozzle. Through the nozzle, with some velocity the fluid is coming out. That velocity, let us take it as a v1. Since this is happening at inlet of the blade, so let us consider the velocity also v1. That is for inlet velocity triangle. Okay, so this v1 is nothing but absolute velocity of the jet, and that is the nozzle is fixed. Here the nozzle is fixed, and the velocity with which the fluid is coming out of the nozzle, the velocity with which the fluid is coming out of the nozzle is called as absolute velocity of the fluid at the inlet, and this is denoted by v1, and it makes an angle alpha with the horizontal or to the tangential direction. See, in this case, if you take, see, as we have taken the jet in horizontal direction, but actually if you take the jet is striking in this way, so this is the jet and this is the tangential direction. Tangent, if you draw here, it becomes a tangential direction. So it makes an angle of alpha with the tangential direction or with the horizontal. Then next, this velocity v1 making an angle alpha with the tangential direction or with the direction of motion of wave. So here, look at this figure here. The jet is striking in this way. The vane is moving in this direction. Okay, the vane is moving here. From this diagram, we get VR1, that is the relative velocity of the fluid, there is a relative velocity of the fluid, and that means with this velocity it comes inside the blade passage, means here from the nozzle the jet is coming out with a velocity v1. This is called absolute velocity, but the jet is not striking the vane with this velocity. This will strike with a velocity called VR1, that is relative velocity, because the vane is also moving here. Okay, the vane is also moving and the jet is also moving. Both are moving. Then we have to take the difference of these two, that becomes relative velocity, that is represented by this one. Okay, so this is absolute velocity and this is the vane velocity. Just to shift this to here and keep here, this becomes u1. Whatever u is here, the vane is moving, just it is kept here. So like this, see, I'll draw here. So this is the jet velocity v1 and this is the vane velocity u1. Okay, then the difference of these two, this is what we call as the vector difference of these two, that is we get relative velocity v1 minus u1 vector nature. Just you shift there and I'll draw next like this. This is v1, the same magnitude and direction. I'll shift here and keep here. This will become u1. Then this will be, this represent VR, relative velocity. So this is what we call as a velocity triangle. This is the resultant. So this is called a resultant, that is this is joined by head of that is a tail of relative velocity is joined with the head of absolute velocity. Okay, this represents the relative velocity and this entire triangle what we call as a velocity triangle. Then next, this one, so we have placed the tail of vector v, like here as I said in this one, the tail of vector v, this one, the tail of vector v, this is the tail. They take this as a tail in vector and this is the head. So place the tail of vector v at the head of the vector u. So at the head of vector u, that is u equal to that is a plate velocity and v equal to the absolute velocity. Then we have to construct the velocity triangle like this. Actually it is like this, v1, then this will be u1, then the third will be like this, this will be what, vr1. So what I have done here, just I have shifted this one here, same magnitude. Then you have to join this one, this will be vr1, this is v1 and this is u1, this is vr1. Okay, like this. Then from this diagram, as I said, that vr1 is the relative velocity of the fluid. That means with this velocity it comes inside the blade passage and moves through the blade passage. In the blade passage, so as it is moving with this velocity in the blade passage, there could be a frictional resistance in this blade passage. There could be a frictional resistance. Due to that, when the fluid comes out of the blade, it may have a different relative velocity, that is VR2. If you take this is a VR1, then it glides over the surface like this, like this, and it comes out with this velocity. This is called VR2. This velocity is called VR2. And though, look at this figure, though the blades move in a circular path, these blades will be moving in a circular path. This is not moving in a linear path. Though the blades are moving in a circular path, but for a small amount of time, if you consider a very small amount of time with which it is in contact with the fluid, this blade with which it is in contact with the fluid, we will assume that it is having a linear motion like this. We'll assume it is having a linear motion in the direction given by the arrow, that is this one, in the direction given by the arrow. This is given, that is u1, and it is not having a linear, actually it is not having a linear motion, but for a small amount of time during which the fluid jet strikes on it, it will be having a linear motion. Then it takes the rotary motion. Okay, I hope you understood this one. I'll repeat, though the blades move in a circular path, actually it will be moving a circular path, but when we draw a velocity triangle, we are taking in a linear path. So initially, for a small amount of time, a very small amount of time, when it is in contact with the jet, it will first move linearly. The moment the jet strikes, it will move linearly with velocity u1, then it takes the rotary motion actually. Okay, so here we have drawn, this is a v1, then this is the motion of blade, then this motion of blade we have shifted here and kept here like this. Then the difference of these two will give you the relative velocity. Then the triangle ABC is a inlet velocity triangle. Okay, triangle ABC is an inlet velocity triangle. Then as the jet is entering with a relative velocity VR1, and assuming this blade passage is having a very smooth, there is no any frictional loss here, and if at all the frictional loss are present, and that whatever the jet is coming out of the blade passage, it will come with the different velocities. Okay, so here I am considering the inlet velocity, that is a relative velocity VR1, and the outlet velocity is VR2. Okay, again the blade is taking a linear motion. Again at the outlet also you have to take the linear motion. Just mark this is a u2, this one is u2, then join this to this one, you have to join this one. Then triangle EFG represents outlet velocity triangle. Okay, outlet velocity triangle. So next, again this triangle represents the inlet velocity triangle, and this represents the outlet velocity triangle. Okay, so I hope you understood this much. Then again the next part of this video, just I'll draw this triangle once again at the inlet as well as at the outlet. Again I'll continue this one. So in the next part of this video, so I'll draw this one as well as this one, but I hope understood the basic concept how to draw velocity triangle at inlet as well as at outlet. Here we'll discuss how to construct a velocity triangle and all. So here in this particular figure, so this figure represents a jet of water striking moving curved plate. So the jet is coming out of the nozzle and it is striking the moving curved plate or the weight tangentially to the shaft. We can call it tangential to the shaft of the turbine like this. This is the turbine, and if you take the perpendicular to this, if you take this perpendicular to the shaft, that represents the axis of the turbine, and it is striking in this direction, means this will be the tangential direction, tangential to the shaft. So the jet is striking tangentially at one of the tips. As the jet strikes tangentially, then the loss of energy due to impact, of the jet will be taken 0. And in this case, as the plate is also moving, the velocity with which the jet of water strikes is equal to the relative velocity. The velocity with which the jet of water strikes is equal to the relative velocity and relative velocity of the jet then with respect to the plate. Also, the plate is moving in different directions. This plate is moving in different directions of the jet. Then the relative velocity at inlet will be equal to the vector difference of the velocity of the jet and the velocity of the plate. So this, the relative velocity to be taken, the vector difference of the velocity of the jet and the velocity of the vane. And as we know the addition of vectors, how the vectors can be adding. See, the addition of vectors as we were discussing previously. So that is a triangle rule for the addition. That is a head to tail, you can call it as a head to tail. Here we take head to tail. Since the jet is striking in this direction like this with a velocity v1 and the vane is moving in this direction with a magnitude u1. Jet velocity is v1 and the vane velocity is u1. So we are taking the vector difference for the relative velocity. So as we know the definition of vector, the vector will be having both magnitude as well as the direction. So here the arrow represents the head, this represents the head, and this represents the tail. Then how to add these two vectors? Just you join the tail of first vector to the head of next vector. So this gives you what? VR1. Then the resultant is what here? The resultant is V1, that is U1 bar plus VR1 bar. Then if you want VR1 vector is equal to V1 vector minus U1 vector. Then instead of keeping this vector here, if you shift that vector, this is giving a magnitude and direction v1, and this vector you just shift and keep here with the same magnitude, this will be u1. Then the join these two, this will be vr1. Okay, so this can be drawn at the inlet of the blade here. Now same way of followed here and the drawn. As we know, the jet of water is coming out of the nozzle with a velocity v1. Okay, so then the blade is moving with a velocity u. Since we are drawing the triangle at inlet, so let us take the velocity at the inlet tip. This is the inlet tip and this will be the outlet tip. And this vane is moving, as I explained earlier how it moves. Okay, and this velocity is been taking u here, and these jet as well as the vane both are having direction as well as the magnitude. And let us shift this vector and keep here with the same magnitude and direction we have shown here, that is u1. Then the difference of these two will be the VR1. With this velocity the jet is entering into the blade passage, and we have assumed the blade passage is very smooth. There is no any frictional loss here, and whatever velocity with which the jet entering into the blade passage, it will glide over the surface and exit with the same velocity, and it is mentioned here at the outlet that VR2. Okay, if there is no loss in the blade passage, then VR1 is equal to VR2. If any losses, then VR1 is not equal to VR2. Then how to draw the inlet velocity triangle, and it will be having a various components, and from the inlet velocity triangle finally we have to calculate the force exerting by the jet on the vane as well as the work done by the jet. So you look at the inlet velocity triangle, the various components are being drawn, and let us understand one by one and a way to also understand the construction of velocity triangle. Now how to construct this velocity triangle? As we know, the jet is coming with a velocity v1 and it is hitting the blade, and the blade will be moving with a velocity u. Then the difference of the two to be taken as relative velocity, and these three components typically represents what? The velocity triangle. By having these three components we can construct the velocity triangle, that is v1, vr1 and u1, that is blade velocity. So let us look at the inlet velocity triangle. Take a point A and draw a line AB, and you mark a B on the tip of the blade. Take point A and draw a line AB and B to be taken at the tip of the vane. And this AB line should be having a magnitude of V1. And this AB is equal to V1. And this will be having both magnitude as well as direction. And this V1 will be making an angle of alpha with the horizontal line. Okay, this V1, first you have to draw that V1 is equal to AB, then the AB line, that is AB is equal to V1, and V1 making an angle of alpha, and this alpha is called as nozzle angle, or the angle between the direction of the jet and the direction of the jet and the direction of motion of the plate, and this is also called as a guide blade angle or nozzle angle, this alpha. The next, draw a line AC. As I said, this vane is moving in this direction, then we have shifted this vector and kept here, that is we have kept the tail of the plate vector to the, joined the tail of the plate vector to the tail of the absolute velocity. Okay, so we have kept here the same magnitude and direction. Draw a line AC, the mark here AC, and join C to B, that is draw a line AC, and that AC is equal to magnitude U1, and join C to B, and CB represents the relative velocity. CB represents the relative velocity, that is VR1 of the jet, that is at inlet. If the loss of energy at inlet, due to impact is 0, then the CB must be tangential direction to the vane at inlet. This CB must be tangential direction to the inlet. Just to extend and draw tangential to the vane and join for the horizontal line, and this angle represents theta. Then this theta is angle made by the relative velocity with horizontal. Alpha is angle made by the absolute velocity with horizontal, and theta is the angle made by the relative velocity with horizontal. Then next, from B, draw perpendicular BD. From B, draw a perpendicular BD meeting the horizontal line AC. This horizontal line AC, this you have to draw a perpendicular line from B, and that line should meet the horizontal line AC. Then produced at D, then BD represents, this BD represents the velocity of flow, VF1. the velocity of flow Vf1. Then AD represents the velocity of whirl at inlet. This is VW1. This is called whirl velocity VW1, and this is velocity of flow, that is the flow velocity at inlet, Vf1. Then angle BCD is theta, that is vane angle at inlet. This angle equal to this angle and this angle. Okay, now this VW1 is a whirl velocity at inlet, and because of this velocity this vane gets rotary motion, and because of this velocity the fluid enters into the blade passage. This is called a flow velocity, and VW1 is nothing but the component of V1. VW1 is a component of V1, that is nothing but V1 cos alpha. So look at this figure. I written here VW1 is V1 cos alpha, that is component of V1. So this V1 is making an angle of alpha. So VW1 is nothing but the whirl velocity. Whirl is rotary motion. Then VW1 and Vf1 are the components of V1 in horizontal direction as well as perpendicular direction. So VW1 is V1 cos alpha and Vf1 is V1 sin alpha. This V1 is been resolved into two components. So one, so that is one in perpendicular direction and one in horizontal direction, like this. This V1, if you want to resolve, you will get one component perpendicular like this and other you get horizontal. The same, we are just shifted here and drawn here, one horizontal and one perpendicular. So we have got VW1, that is V1 cos alpha, and Vf1 as V1 sin alpha. This triangle, what it represents? Inlet velocity triangle completely. Okay, so try to understand this one. So initially we have to draw V1, then we have to draw U1, then join, that is draw a line CB, joining C, that is C to B, that represents VR1. Then the resolve this V1 in horizontal as well as the vertical. The horizontal component represents the whirl velocity VW, that is V1 cos alpha. The vertical component represents the flow velocity, that is V1 sin alpha. And this VR1 making an angle of theta, that is a vane angle at inlet, and alpha is called as a nozzle angle or the guide blade angle. So this triangle ABD represents the inlet velocity triangle. I hope you understood this one. Similarly, draw outlet velocity triangle. Then as the jet enters the blade passage, it will not enter with this velocity, that is with absolute velocity, it will enter with relative velocity VR1. Then it glides over the surface, then it exits with velocity VR2. Then how to draw the outlet velocity triangle? If vane surface is very smooth, if you are assuming this is a smooth, if there is no losses at all here, then the energy loss due to friction will be 0 here. Thus VR1 is equal to VR2. Whatever velocity with which the jet is entering, here the jet is entering with VR1, with the same velocity it comes out. Hence VR1 is equal to VR2. Because we have assumed this vane surface is very smooth. If there is a loss due to impact or there is any frictional loss here, then this VR1 is not equal to VR2. These two will be of different velocities. Since here we are assuming this surface is smooth and there is no loss at all here, hence VR1 is equal to VR2. And VR2 will be in a tangential direction. Again, this VR2, the relative velocity will be in a tangential direction to the vane at outlet. So tangential direction to the vane at outlet. Then how to draw this velocity triangle at outlet? This triangle represents at outlet velocity triangle. Draw a line easy. So mark this tip. This tip is outlet tip. This is inlet tip. This is outlet tip. Water will enter in this like this. Then it exit like this. So where the water is entering inside the passage, that is called the inlet tip. Where the water is exit, that is called outlet tip. So mark point E here, then draw a line EG in the tangential direction of the vane, in this direction, in the tangential direction of the vane at outlet, and cut this line by a magnitude of VR2. Okay, draw this line EG, then cut this line by a magnitude VR2. Then from G, draw a line GF like this. Draw a line GF from this point. Draw a line GF. Here I have marked as a F. Here I have marked as a F. In the direction of the vane at outlet. In the direction of the vane at outlet, and is equal to U2. This one is equal to U2. This also having a velocity at outlet. So here, look at this one, this figure. So this is the inlet tip where this blade is receiving the jet force here, inlet tip. When it moves along, when it starts moving, this also starts moving. Okay, when it rotates, both tip will start rotating, inlet tip as well as outlet tip. Okay, so this is the direction of vane, and draw a GF of magnitude U2. And the velocity of the vane, and this U2 represents the velocity of the vane at outlet. Join EF, then you join EF from E to F, you have to join, and that represents the velocity of the jet. When you join EF, this represents the velocity of the jet V2 at outlet, and it is having a magnitude and a direction both, that is V2. Then from E, again from E, draw a perpendicular line. You have to draw a perpendicular line from E to meet the line GF. You just extend this line and draw a perpendicular line from E to meet the line GF produced at H. So this from E you have to draw perpendicular up to the line GF, and which is produced at H. Then EH and FH, EH and FH represents the velocity of flow, that is a VF2 represents the velocity of flow and the velocity of whirl at outlet respectively. Again, this VF2 and VW2, they are nothing but the component of velocity 2 at outlet V2. It will be having a beta angle made by V2 with horizontal is a beta. Then VW2 will be V2 cos beta, and VF2 is a V2 sin beta. So VF2 represents the velocity of flow at outlet, and VW2 represents the velocity of whirl, that is the rotational velocity at outlet. Then angle pi, see here angle pi, it is marked here. It is angle made by the relative velocity at outlet, and that is called vane angle at outlet. And the beta represents angle made by V2 with the direction of motion of vane at outlet. That is angle made by the V2 with the direction of vane at outlet. And pi is called as vane angle at outlet. And the triangle EGH represents the velocity triangle at outlet. Okay, I hope you understood these triangles. So with these triangles, now we have to derive the equation, that is force exerting by the jet on the vane. So considering these two triangles, inlet as well as outlet. So here the pi is marked, that is a vane angle at outlet, and this is beta, and this angle we get, that is opposite angles what we get here, and this also beta, and this angle what we get, beta minus pi, beta minus pi. Okay, so I hope you understood this triangle. So this is very, very important, this triangle. So beta minus pi, where I mark, just look at that figure. Then I marked a beta angle. Beta is the angle made by V2 with the direction of motion of vane, and the pi is the angle made by the relative velocity at outlet, which is the horizontal. Okay, so here Vf2 represents the velocity of flow in at outlet, Vw2 velocity of whirl at outlet. Okay, so here I have written V1 is the absolute velocity of jet at inlet, U1 is the velocity of the plate at inlet, Vr1 is the relative velocity of jet with respect to the plate at inlet, alpha is the angle between the direction of jet, this is for inlet velocity triangle, and the direction of motion of the plate, also called the guide blade angle or the nozzle angle, and the theta represents the angle made by the relative velocity Vr1 with the direction of motion of the plate at inlet, also called vane angle at inlet. Then Vw1 and Vf1, the components of absolute velocity of jet V1 in the direction of motion and perpendicular to the direction of motion of vane respectively. And similarly Vw1 is nothing but V1 cos alpha. It is also known as velocity of whirl at inlet acting tangential to the shaft or to the shaft axis, that is tangential components of the absolute velocity at inlet. Then Vf1 is V1 sin alpha. It is also known as velocity of flow at inlet, and that component is axial component of absolute velocity at inlet acting in the direction of axis of the shaft. Similarly, outlet velocity triangle, V2 represents the velocity of jet leaving the vane or absolute velocity of the jet at outlet of the vane. Then U2 is the velocity of the vane at outlet. Vr2 represents the relative velocity of jet with respect to the vane at outlet. The beta represents the angle made by the velocity V2 with the direction of motion of vane at outlet. And the pi represents angle made by the relative velocity Vr2 with the direction of motion of vane at outlet, and also the called vane angle at outlet. Then Vw2 and Vf2, the component of velocity V2 in the direction of motion of vane and perpendicular to the direction of motion of vane at outlet. And Vw2 can be taken V2 cos beta. It is also called as the velocity of whirl at outlet. And Vf2 is V2 sin beta. It is also called velocity of flow at outlet. The triangles ABD and EGH, that is this triangle ABD, triangle ABD and EGH are called as velocity triangles at inlet as well as at outlet. Hence, these two velocity triangles are used to find the force experienced by the jet and work done by the jet. So further, next we have to derive the equation by utilizing the velocity triangle at inlet as well as at outlet. So the construction of velocity triangle is very, very important here. So typically it consists of absolute velocity, vane velocity and relative velocity. So once we construct with these three components, then next will be the resolution. You have to resolve the absolute velocity at inlet as well as at outlet, then you will be getting the components finally. So you will be getting the once you resolve the absolute velocity, you will be getting Vw1 and Vf1 at inlet, that is velocity of whirl as well as velocity of flow. Similarly at outlet also you have to resolve you will be getting VW2 and VF2. They are called as a velocity of whirl at outlet, velocity of flow at outlet. Then once we know these all things, so then we can easily get the force exerting by the jet on the vane and work done by the jet on the vane. So with this concept of velocity triangle, I hope you understood this concept. Try to understand and just practice to draw the velocity triangle, how to draw the velocity triangle and all. Practice it and understand this one. Okay, so in the next part of this lecture I'll be deriving the equation, that is Fx, and work done by the jet and efficiencies. Okay, we have discussed this velocity triangle will be very much useful in turbo machineries, where the velocity triangle or the velocity diagram is a triangle representing the various components of a working fluid in a turbo machines. And the velocity triangle may be drawn both at inlet and outlet sections of any turbo machines, and from the velocity triangle we can analyze the velocity of the fluid, and the vector nature of the velocity is being utilized in this particular triangle. And most basic form of velocity triangle consists of the absolute velocity V, then relative velocity VR, and the blade velocity U. And about the construction of a velocity triangle we have discussed in previous lecture. Please go through that lecture and try to understand the construction. And after construction of velocity triangle, how the force experienced by the jet and work done by the jet can be calculated. Force experienced by the jet and work done by the jet. So this is very important derivation. And considering the velocity triangle, you have to construct a velocity triangle at inlet and outlet of the blade, and from the velocity triangle you have to calculate the force experienced by a jet as well as work done by the jet. And at inlet velocity triangle, you know the various components as explained earlier, where V1 at inlet velocity triangle, V1 represents absolute velocity of jet at inlet, and angle alpha is angle made by V1, that is called guide blade angle, or angle at which the jet enters the vane. Then theta represents the inlet blade angle, that is a blade angle at inlet, and VR1 represents a relative velocity at inlet, and VW1 is a whirl velocity at inlet, and VF1 the flow velocity at inlet. These VW1 and VF1 are the components of V1, the components of V1 in horizontal as well as in vertical direction. And the jet will enter with a velocity VR1 into the blade passage, and it will be making an angle of theta with the horizontal. And when you resolve this VR1, one in a vertical direction and one in a horizontal direction, you will be getting VR1 cos theta and VR1 sin theta. Okay, so VR1 cos theta is the horizontal component of VR1. We get VR1 cos theta as well as VR1 sin theta we get. Similarly, at outlet velocity triangle, look at the outlet velocity triangle. Again, there are various components there. There the pi represents the outlet blade angle, that is blade angle at outlet. Then VR2 represents the relative velocity at outlet, VF2 represents the flow velocity at outlet, VW represents the whirl velocity at outlet, and V2 is the blade velocity. And it is very easy to construct the velocities triangle at inlet as well as at outlet. Once we construct the velocity triangle at inlet and outlet, then with respect to these two triangles, we have to calculate the force experienced by the jet on the vane, that is force experienced by jet on the vane. We have to apply the impulse momentum principle here also. So applying impulse momentum principle, or impulse momentum equation, then force in x direction. So Fx will be a rate of change of momentum in x direction. Then Fx can be written mass per second into bracket initial velocity minus final velocity. So here mass of fluid striking the vane per second. Here mass of velocity or mass of fluid striking the vane per second. So equal to mass per second, which is equal to as we know density equal to mass by volume, so we can write density into area of jet into velocity. We get density into area of jet into velocity. We can get rho is density is a rho into area into velocity. Here velocity to be taken relative velocity. With this velocity the jet is entering into the blade passage. If you look at here, so it will be entering with relative velocity, not absolute velocity, because vane is also moving, so it will enter with a relative velocity. Hence we have to take the relative velocity, that is VR1 at inlet. So this is a mass per second. We have to substitute here. Then Fx will be rho a VR1 into bracket initial velocity. So here we have to take the initial velocity with which the jet, initial velocity of the vane. So since it is entering with VR1, so like this, so I'll draw here. So jet will be entering with this velocity. This is VR1, which is making an angle of theta here. Okay, then we want force in x direction. Force in x direction, you have to resolve this VR1, one vertical and one horizontal. When you resolve this you get VR1 sine theta, and this is VR1 cos theta. Okay, then initial velocity in x direction, we have to take VR1 cos theta. So here I'll write VR1 cos theta initial velocity minus final velocity. Final velocity again same, at outlet velocity triangle you have to look. So this is the initial velocity, then outlet velocity you have to take VR2 cos pi. This is the VR2 exiting. Again you have to resolve at outlet. Similarly here at outlet, when it is exiting like this, VR2 and this is making an angle of pi here. When we resolve this one, this is one component, this is other component, you get here VR2 cos pi. Okay, I hope you understood this one. Then you write final velocity as minus, again this is opposite to the direction of incoming jet. So this one opposite to the direction of incoming jet. This is going opposite. The incoming jet is in this direction. The incoming jet is in this direction, and the jet leaving in opposite direction. So you have to write minus of minus VR2 cos pi. Then, but from velocity triangle, that is figure, velocity triangle figure, if you look at a velocity triangle figure, what is VR1 cos theta? See, what is VR1 cos theta? If you look at this velocity triangle, this is a VR1 cos theta from here to here. So VR1 cos theta is what? VW1 minus U1. VW1 minus U1. So from VR1 cos theta will be VW1 minus U1 from inlet velocity triangle, and VR2 cos pi is what? VR2 cos pi is what? You just look at the outlet velocity triangle here. So one we have taken this one. So VR2 cos pi it is. This is actually VR2 cos pi. This is VR2 cos pi. this component. Then this one, when we resolve this one, we are resolved here. Just look at this figure. So if I shift here, you will get like this triangle. Then this is VR2 cos pi. Okay, VR2 cos pi. That same I written here, VR2 cos pi. That is nothing but U2 plus VW2. U2 plus VW2 from outlet velocity angle. U2 plus VW2. Okay. Then substitute in the above equation, we get Fx equal to rho A VR1 into bracket VW1 minus U1, then plus U2 plus VW2. And since here, since U1 equal to U2, so if you take the velocity of the blade at inlet as well as at outlet, that is the velocity of the blade, if you take, so this is the disc or the impeller, it is the shaft, it consists of blade like this. So if you take this blade, one blade, this is the inlet and this is the outlet, when the jet strikes this one, this will be moving forward. Along with this, this also moves forward. So both the velocities are same here. This end and as well as this end, the velocities are same. So considering the velocity of vane is same, so U1 equal to U2 equal to U, velocity in the direction of jet of motion, and when U1 equal to U2 is equal to U, also VR1 is equal to VR2. So here VR1 is equal to VR2 means we have assumed the blade passage, this blade place is very smooth. Whatever velocity with which the jet is entering, the same velocity it is leaving. So VR1 is equal to VR2. Then after this, we have assumed U1 equal to U2 equal to U and VR1 is equal to VR2. Then what the equation we get finally? When you substitute in the above equation, we get Fx equal to rho A VR1 into bracket VW1 plus VW2. So here both will get cancelled here. When you are assuming U1 equal to U2, then these two get cancels. You will get rho A VR1 VW1 VW2. Then this is the equation what we get. Okay, so after this one, then next what we get, this is the force in x direction. VW1 is the whirl velocity and VW2 is the whirl velocity at VW1 is whirl velocity at inlet and whirl velocity at outlet. Then some conditions here, conditions to be considered, that is condition 1, when beta equal to 90 degree, when beta becomes 90 degree, when beta becomes 90 degree in this figure, just look at this figure. So if you take the angle beta here, this angle beta is acute angle. When it becomes 90 degree, this beta, just I'll draw here, just look here, when that angle becomes 90 degree, this one like this is like this, like this. Okay, so this is the U, that is U2 we are taking at outlet. When this becomes 90 degree beta, when beta becomes 90 degree, and this is, and this will be taken in this figure, when beta becomes 90 degree here, see, when beta becomes 90 degree, so this V2 is equal to VF2, V2 will be equal to VF2, V2 is equal to VF2. And when beta becomes 90 degree, what about whirl velocity? Whirl velocity get vanished here, will not get whirl velocity here, so it get merged. So earlier it was like this, now when it becomes a 90 degree, so whirl velocity will be 0, so VW2 will be 0 here. When beta is 90 degree, V2 becomes VF2 and this is pi, and VW2 is 0. Then the above equation becomes Fx will be rho A VR1, that is VW1 only, when beta is 90 degree. Second case, when beta is greater than 90 degree. So this case is, this one is when beta is less than 90. This case is when beta is 90, when beta is 90 or more than 90 degree. So if this beta angle, beta is what? Here beta is, what beta represents angle made by the velocity v2 with the direction of motion of wave. Angle made by the velocity v2 with the direction of motion of wave. Okay, so this beta is angle made by the v2 with direction of motion of wave. When this beta is greater than 90 degree, so how will be the figure? Will be like this figure, and this will be as it is, that is VR2 will be as it is, and V2 will be like this. This V2 becomes like this. This is to be V2, and this vertical component will be as it is, that is VF2, and this whole will be U2. From here to here is a U2, and this will be what? VW2, and this will be component of VR2 cos pi. So now here you have to consider this one, this angle made by V2 with horizontal. I am taking angle made by V2 with horizontal which is greater than 90 degree. So previous angle made by V2 with horizontal was 90 degree, and first case was angle made by V2 with horizontal was acute angle less than 90 degree. So for less than 90 degree, this was the equation we have got, and for 90 degree the whirl velocity get vanished, and if beta is more than 90 degree. So these cases are very important while solving a problem. If beta is more than 90 degree, this is angle at which the jet is exiting from the vane. So in problem they'll give the jet is exiting from the vane by making an angle of 90 degree, or by making an angle of less than 90 degree or more than 90 degree. If V2 making an angle with horizontal is greater than 90 degree, so what we get here, Fx will be, then Fx will be what? If you want to calculate Fx, what we get Fx here, rho AVR1, then you will get VW1 minus VW2 we get. VW1 minus VW2 we get. Okay, so we get minus VW2 here when beta is more than 90 degree. This is the equation we get finally. So in general we can write Fx equal to rho AVR1 VW1 plus or minus VW2. This is the general equation. So depending on the value of beta, that is angle made by V2 at outlet, you can write plus or minus, or some terms get vanished, that depends. Okay, so this is the final equation, that is force in x direction. Then work done by the jet. Work done by the jet is work done per second, work done by the jet. Then we write Fx into velocity of plate. Then Fx we know, that is rho AVR1 into VW1 plus or minus VW2 into U. So this is work done per second. Then efficiency of the jet, if you want to calculate efficiency of the jet, then work done per second output by input, kinetic energy per second, and here kinetic energy per second, again as usual you have to take kinetic energy per second will be half mv square. This is a formula, but this is per second, we get rho A V cube. The same formula to be applied here. So with this you have to calculate kinetic energy per second, then work done per second is this one, then finally you get the efficiency. I hope you understood this derivation. So very important, the derivation here. So only thing is the conditions what we apply here. When beta is more than 90 degree, you will get a VW1 minus VW2 here. So when beta is less than 90 degree, so this was the equation, we got the VR2 cos pi. So this VR2 cos pi, here look at this figure. So how we have got the minus sign here. If you take VR2 cos pi, what we write VR2 cos pi here? VR2 cos pi will be what? U2 minus VW2. So when you substitute in this equation here, so Fx will be what? We get rho a VR1 in this like this, rho a VR1 VW1 minus U1, because U1 equal to U2 we're having. So U1 U2 get cancels, we get VW is VW1 minus U1, VW1 minus U1, then plus U2 minus VW2 we get, but U1 equal to U2, this just cancels, then finally you get rho a VR1 VW1 minus VW2 we get when beta is more than 90 degree. So I hope understood these conditions. So very important conditions. Okay, and derivation is also very important. Force experienced by a jet, many a times the question asked in an exam, and also work done by the jet. Okay, so taking velocity triangle into account, you have to get the force exerted by the jet in x direction, and when beta is less than 90 degree, and when beta is 90 degree, this is the force, and when beta is more than 90 degree, then finally this is the efficiency of the jet. Then work done per second you have to calculate. Again, in general the equation can be written like this. Okay, thank you.